welcome to the PhD defense. Yun Hoi Yun. Okay, and Lock Yu is the supervisor. Start.
Okay.
So try to limit to 40 minutes.
40 minutes?
Yes.
Okay.
The first thing is to be a researcher, you need to know how to limit your talk.
I thought I have an hour, but okay, I'll try to make it 40-45 minutes. Okay, anyway, let me start. Okay, so good morning everyone. Thanks for coming to my oral defense of my PhD at the Division of Physics and Applied Physics in NTU. So the topic of my PhD thesis is complexity, a study of fractal and self-organized criticality. Okay. So this is the outline of what I'm going to present today. So first I'll provide you with the context of the study, so the motivation behind, so why we are doing those stuff. Okay. So the second one is the introduction. So after the introduction, then I hope I can give you a brief idea of what you should expect from my presentation and what you should learn after you walk out of this room. Okay. And the next two parts are on the main study. The first one is on fractal, and the second one is on self-organized criticality. And after that, I'll provide conclusions and some outlook. Okay. So before I move on to my presentation, I just want to show this quote from a French mathematician, Henri Poincaré. He said that the scientist does not study nature because it is useful to do so. He studies it because he takes pleasure in it, and he takes pleasure in it because it is beautiful. If nature were not beautiful, it would not be worth knowing, and life would not be worth living. Okay, so that's my motto. Right, so this is the context of this study. So very often in nature...
So you agree completely with the assessment?
Well, it's just my motto, so I think that I have an excuse for what I do.
Yeah. Okay. You have no larger ambition and motivation to solve everything useful.
Well, that's why, because Henri Poincaré is really a great mathematician, so I learned from him. Okay, so very often in nature we encounter things like very simple rules, very simple rules, and it goes and those rules, they go through this thing called black box called the complex systems, and the outcome is something like emergent behavior, complex behavior, and we call that complexity. So there are two examples. There are two parametric examples that physicists have discovered. One is self-organized criticality, and the other one is on fractal. So you can see the cartoon here for the example of self-organized criticality and fractal. On the left, you can see a hand playing with the sand pile. So you see the hand dropping sand particles on top of the sand pile. So what is special about it? So in this system, you can see this system has many degrees of freedom. So you can think of each particle as one degree of freedom. So there are overwhelmingly large, many of them. Okay, and these degrees of freedom, they interact with one another because you consider the sand pile as one system. So you call that internal interactions. Okay, and in the case of fractal, so in this cartoon you can see it is a computer-generated graphic of a fern leaf. So you can see the cell similarity properties. So you look at the whole, you look at the leaf as a whole, and you capture the pattern, and now you focus on a small branch, and you can see the same pattern again. So that's what we mean by cell similarity. So it's similar to itself. And one feature of this kind of object is that it has non-integer dimension. So usually, intuitively, we know that the object we have like 1 dimension, 2 dimensions, or 3 dimensions. But these very strange objects, they can have non-integer dimension. But the common feature between these two examples, it is the scale invariance. So meaning the invariance at any scale. So in the case of fractal, it is very easy for you to imagine what is scale invariance in this case. So it is just the cell similarity feature. So it is at any scale, then you see the same pattern again. Okay. But in the case of self-organized criticality, it's a little bit harder. So you need to go a bit further into my presentation in order to appreciate what is meant by scale invariance in this case. But I can tell you now that the scalar invariance in this Salomon Schwier quantity is characterized by the power law distribution of the event size, which you will see later. Okay, so that is the context of my study. And throughout this project, at the beginning, we wanted to study complicated fractal objects. We studied and also to study the self-finite critical models to study their scaling behaviors and investigate the universality class. Okay, and that is the aim at the beginning. So after the project, we have achieved a general fractal generator, which I will show you later, and we perform an in-depth study of the Abelian-Manner model on various lattices. Okay, and from that study, we discover the general scaling behaviors of the model, and we gain more insight into the understanding of the universality. And with those developments, we make advancement towards the analytical SOC, which is a current focus in the literature at the moment. Okay, so now let me move on to the first part on fractal. So in his classic book, Fractal Geometry of Nature, Mandelbrot, he wrote that clouds are not spheres. You look into the sky, then you see clouds. They're not spheres. Mountains are not cones. Coastlines are not circles. Bark is not smooth, nor does lightning travel in a straight line. Okay, so we know that we observe that many complex objects like clouds, tree branches, or terrain, which cannot be described repeatedly by regular geometry, and hence we need a new kind of geometry to describe them, to study them, and that's why Mandelbrot came up with this thing and called that fractal geometry. Okay, so now you ask, okay, what is a fractal? So if you ask me a fractal, okay, I can tell you these two things as you have seen earlier. That is the non-integer dimension and the self-similarity. So for the non-integer, in order to understand the non-integer dimension, you need this concept of the generalized measure or the Hausdorff measure. So you can think of this thing. It is a very mathematical concept, but I can tell you it is just a generalization of your intuition of the length, surface area, or the volume. Okay, and with the aid of that Hausdorff measure, you can get the value of the measure in generalized dimension, not just in 1, 2, 3 dimension, but you can get in some arbitrary non-integer dimension. And from there, then you can obtain that the correct measure of the object has non-integer value. So that's where you get the non-integer dimension of the object. And self-similarity, okay, I hope it is straightforward for you to imagine this thing. When we have two types, one is strictly similarity, and the other one is statistically self-similarity. Okay, and the term itself, I think that's how I explain. Okay, so roughly we know what a fractal is, right? So how can we generate fractals? So in nature we have observed things like trees, so we see examples of fractals. So now we theorize, so how do we generate them? So in the literature throughout the years, different methods have been developed to generate fractals. So there are the four most commonly used. So the first one is the IFS, the iterative function system. The second one is the recursive operation. The third one is the linear manner system. And the fourth one is the chaotic dynamical system. So out of the four, I just want to make a remark on this linear manner system, which you will see my reference later to that system. It is actually quite an interesting system because it was invented by a Dutch biologist. You see, he published his paper in the journal Theoretical Biology long time ago, half a century, I guess. Okay, so actually his idea was that he wanted to invent some system to draw plants because he's biologist, so he draw plant and he found this system, and eventually he said, oh, okay, this system can generate a lot of fractals. Okay, then actually there's a very good book on that subject published by Springer. Okay, so okay, now this is an example of the generating fractal from the recursive operation. So it is very simple. So you start with the line segment, one-dimensional line segment, and the operation is that you divide that segment into you divide this line into 3 equal segments. Okay, so I mark down here, and the operation is that you remove the middle third. then you replace that middle third by 2 new segments, so that the whole thing makes up an equilateral triangle without the base, because you removed the base already. And you keep doing that for each of the newly created segment. So you keep doing that, and you get this thing called a Koch curve. Okay, so interestingly, well, you can play around with this thing, then you put these 3 Koch curves together, and you can get this thing. I hope you know what it is. It is called a Koch snowflake, right? Looks like. So that's more or less the background of the fractal. So in my study, I came up with a novel idea to generate fractals with tunable dimension. So the idea is that instead of using the line segment as I just showed you, I use an arc. Okay, so I define my arc, my geometric arc as an open arc with angle alpha. This is the center that you can get the angle and radius arc. So this is the definition of an arc. So the operation is that you divide the arc into small segments, and you replace each of the part of the arc by a new smaller arc. And there are 2 ways you can do that. You can replace the new arc by using the with the orientation inward, or with the outward orientation. Okay. So in this system, there are 3 parameters you can play around with. The first one is angle. This angle. The n is the number of arcs. Okay. So how many arcs you divide your mother arc into. Okay. And the omega means the orientation of the arc. So in this case, it's inward and outward. Okay, and there are 3 types of rule. So single means you keep applying the same rule over and over again through every iteration. Multiple rules, so you have a set of rules, so you keep applying the same set that go to the next iteration, then another set, and random, so you just apply the rules randomly. Okay, so with this system, it is interestingly found that by choosing the correct combination of the 3 parameters, alpha, n, and omega, so we can obtain back the classic fractals that were discovered earlier in the literature. So you know this is the Koch curve that I showed you earlier, the highway, the Levy, the Sierpinski, and the Eisenstein. So you see the value of the alpha and the number of arc I'm dividing to, and the omega. So the +1 means inward replacement, and -1 means outward. If you want to get more like why I obtain plus and -1, like you can refer back to my thesis. So there's a mathematical derivation of this thing. So now let me show you an example. So these are the 4 examples that I show in this table: the Koch curve, the highway, Levy, and Sierpinski. Okay, so this is the Koch curve. You know the rule already. So let's see how my arc system can generate that thing. Okay, so you remember, so recall the rule. So alpha is 2 pi over 3, and 2 segments, and the orientation both inward. So you see here, I start with an arc. So you see the angle of that arc is 2 pi over 3. So divide into 2 segments of equal size, and then replace them with a new segment of the same angle with the orientation inward. Okay, so I hope this thing works. Okay, so you can see that's the rule, so I can obtain that thing. And similarly for this highway dragon, so you have a piece of paper, a right triangle with the 2 equal edges. Okay, so you cut them in half and you flip one, and you keep doing the same, so you obtain that after the 4 iteration. So from the arc system, I can also obtain that by using the arc. So I start, you remember the angle is pi. So I have a semicircle, so I divide it into 2 segments and replace one is inward and the other one is outward. So that's why I have +1 and -1. So here you can see the iteration. Okay, so similarly for this Levy dragon, so it's similar to the highway dragon, but the difference that now you flip both parts. Okay, so previous one you just flip one, keep this the same, but now you flip both of them. And from my system, I also have the same. Sorry. Okay. Alright, so this is the iteration that you can obtain this Levy dragon. Okay, but the last thing I find it most interesting, because now you see you have this famous Sierpinski gasket. So the way to construct is you have a triangle and you remove the middle triangle, and you keep doing that and you obtain this pattern. Okay, so recall the table, so the value for the alpha is again pi, so it is a semicircle, so I divide my semicircle into 3 equal segments, one here, one here, one here, and the orientation is inward, outward, and inward, +1, -1, and +1, okay? So let's see the iteration. So we keep doing that, keep iterating, and eventually I obtain the pattern of the species of the CSP gasket. And you remember I have another, the 5th entry, which is for the Eisenstein. I don't have space, but you can. It's actually the thing up there, the logo, and it's actually the sister of this one. I just flip the orientation. Okay, so I just showed you the example how my arc fractal system can generate different fractals. Okay, so now we can measure the dimension of the arc fractals generated by that system. So I have this formula. So if I divide my arc fractals with equal segments, then I can get the dimension of that fractal is given by this, where n is the number of segments that I'm divided into, and the alpha is the angle of my arc. Okay, and another feature of this system that's I think it's blurred, so hope you can see from my screen. Okay, so that's what
yellow, right? You don't use yellow on presentation.
Okay. No, actually this thing is not yellow, somehow it's not shown. Okay, so you see that every time an arc is replaced, so the two endpoints of the arc, they're still there, they're not replaced. So that's why they belong to this invariant center point. And that invariant center point in later part of my work, then see I employ them as a fractal lattices for my study of self-organized recality. So you can see here the green actually belong to the green points belong to that invariant center point. Okay. And another quite nice feature of this the fractals generated by this system is that they can tau the two-dimensional space. Okay, so you recognize this thing as that the Eisenstein fraction of that. So as you can see, this thing actually one copy. This is another copy. One copy, and you tau them together. And if you have many copies, just like you tau your floor, then you just put them together. So they fit. They tau the entire space. And the Koch curve is also similar. Okay, and this subject of tauing space is on quite an interesting subject in the mathematics literature. Okay, so actually that is just to show you the intuitive idea, but we need to prove that actually those objects tau the space. So the idea to prove the tauing is that you show that the boundary they can mesh together. So in one copy, then you mesh them so that they can tau the space. So that's the idea to prove the tauing. Okay, so that's more or less my arc fractal. So just here, I just give a few more examples of what this system can do. So the examples that I showed you earlier, they are for the single rule. So remember, I have a single rule, multiple rules, and random rule. So with this multiple rule, I can generate more complicated fractals. So this is another famous example of this thing called the Sierpinski carpet. So the rules that you have, they square, and you punch the hole in the middle, and you keep doing that, and you obtain this nice, it looks like a carpet, the pattern of the carpet on your floor. Okay, so this system can also generate that pattern. So I start with an arc, then I use multiple rules. So I keep iterating, and about the 8th or 9th iteration, then you can see this pattern of the Sierpinski carpet. Okay, and some more results. Okay, I think I just carry on with one more example here. This is the fractal from the Pascal triangle. So you know the Pascal triangle. So they are a triangle made of the coefficients of the binomial expansion. So you look at this. This is when you have a plus b raised to some power n, right? N is 1, and you have the coefficient 1, 1. Oh, sorry, n is 0, so we have coefficient 1. N is 1, they have 1, 1. N is 2, a plus b squared, so 1, 2, 1, 2, 1. Keep it there. So this is called the Pascal triangle. So actually, you can have a fractal from here and look at this triangle. I'm sorry, you cannot see on this projector, but I'll show you. Okay, so if you check this node with the even number and you leave the odd number alone, okay, so you can get this pattern. You can look at my screen actually. Then you can see this is the pattern of the Sierpinski cascade. Okay, and earlier you have already seen how that is constructed. So I don't really have much time, so more samples, so you can refer to my thesis later. So a few more fractals again. So this is the, now I show you one possible application of the this R fractal system. So I thought a lot about it, and one possible application I could find is the coastline. It is to have this R fractal system as a model for coastline formation. So we know that in coastline formation there are two fundamental processes. So one is erosion by sea waves, and the other one is accretion by the sediment or sand. Okay, so my assumption is that the sea waves hitting the coast leave behind smooth curves that can be absorbed, that can be approximated as arcs. Okay, so the idea is that you can imagine that the evolution of the coastline as the iteration of the fractal. So from there, then you can generate several samples of the coastline. Okay, so that's more or less for the first part on the fractal. So now I move on to the second part, which is on self-organized locality. Okay, so without looking at the footnote, I hope you can recall where this sentence comes from. So who could ever calculate the path of a molecule? How do we know that gradations of words are not determined by falling grains of sand? So Purbach, when he wrote his book, so he found this called that because his model was on the Sandpile model. So okay, writing something about Sandpile, then actually you look at the title, his book is very ambitious, How Nature Works, and the Science of Self-Organized Reality. So this actually fits well to his book. Okay. Anyway, so we know that nature is not in equilibrium. So if it is in equilibrium state, we are dead already. Okay. So it is out of balance or non-equilibrium state, but it is organized in the void state where anything can happen within well-defined statistical laws. So we have very robust statistical laws that can describe many different phenomena. Okay. And in those natural systems, we can find this thing, the scale invariant spatial temporal structures abundantly. Okay, so Purbach in 1987, so he came out with this model, and he called it the science of self-organized reality, and he hoped that this thing can explain different phenomena that we observe in nature. Okay, so now let me give you a very simple example of self-organized reality. So here is the Sandpile model on a two-dimensional square lattice. Okay, so the rule is that when you have an active site, you let it relax, and it relaxes by transferring 4 particles to the nearest neighbor. So the second two lines, so this side loses 4 particles, and each of the nearest neighbor will receive 1 particle. Okay, so this is what the 3 line means. Okay, so now let's see that thing in action. Okay, so now I have this random configuration. It is stable because there is no active site. So now I perturb the system by choosing one site. Let's say I choose this guy, and I perturb it by adding 1 grain of sand on top of it, just like the hand playing with the sandpile you seen earlier. Okay, so now it is 4. So 4 it is active, so it relaxes according to that rule. So you see that it is 4, so we will get down to 0, and each of the nearest neighbor will get 1 unit. Okay, so in the next time step, you see this is 0, so this is 2, 2, 4, 3. But the story does not end there yet, because now you have a newly created active site, which is this guy. So just apply the same thing over and over again. So you arrive at this state, and now you look around and you see, and you don't see any more active sites. So now the system is in a stable configuration. So you see, from this action of perturbing the system at just one side, you see 8 sides are involved, they are perturbed. So from this one to that configuration, we have this thing called an avalanche. Okay, so within an avalanche, we can define 3 main observables. So the avalanche size, which is the total number of topplings, the duration, the total number of parallel updates, and the avalanche area, which is the total of listing size visited. Okay, since I don't have time to go through, so I will come back to this later. So I move on to this thing. Okay, so we know the three observables in our system, so we can find the event distribution. So the event size means the size of the size of avalanche, the duration of the avalanche, and the area of the avalanche. Okay, so Burbach, the three physicists, Bach, Planck, and Weissenfeld, they discovered this model, and they found that the event size distribution of their model, they follow power law. Okay, so the power law is of this very simple form. So you just have the argument is this the size of the event, and you just have one little number up there, which is called the exponent of the distribution. And it's just one number, but it characterizes the entire distribution. Okay, and why this is interesting in engineering, because power law distributions are far ubiquitous in nature. Okay, well, I can tell you where you can find it. You can find it in earthquakes, the distribution of earthquakes, the rain formation, the forest fires, or in biology, you know, the biological evolution, the epidemic spreading of financial markets, and even in our human body, you have the power distribution and the human society as well. Okay, so that's why when Bach and Weissenfeld they discovered this, then they say, okay, this is how nature works. A very ambitious plan. Okay, and this is just one more example to show the correspondence between the sandfire model and natural system like the atmosphere or the Earth's crust. So you know the mechanism. So this has been done in literature and to show the correspondence between this theoretical model and the real system, the real natural system. Okay, so that's more or less the introduction to the background to the self-organized spirituality. So now I move on to my work on self-organized spirituality in my thesis. So in my thesis, I studied this another model. The other model I show you is called the abelian sandpile model, and this model is called the abelian manner model, just another model. But this model was shown to behave much better than the BTW, the abelian sandpile model that I showed you earlier. So that's why this model is a very good object for study. Okay, so the model is defined this way. So you have two steps: the driving and the relaxation. So driving is just the same as the previous model. So you choose so you have a system in the stable configuration, and you choose one side at random, and you perturb by adding one, and you perturb the system by adding one more grain of sand to the system at random. Okay, and the difference between the two models is in the relaxation. So previous model, you see, it is a deterministic relaxation. So each of the nearest neighbor receives one grain. But in this model, every unstable site I relaxes by transferring two particles to its randomly chosen neighbors, possibly rendering the receiving side unstable. Then from there you have an avalanche. Okay, let's see this. So this is an example of the abelian manner model on the line lattice. So let's say I have a lattice of 10 sides. Okay, so you have the initial configuration, and all sides they just have 0 or 1. So it is a quiescence. So now you perturb the system by adding one grain of sand to a randomly chosen site. So in this case, I chose site number 5. So you see, previously it has 1, so I add one more on top of it. So now it has 2. So what will happen, because now 2, so it is active. Okay, it is active. So I draw a random number for the top particle. If I have, let's say I toss a coin. If it's head, then this one will go to left. If it's tail, then we go to right. So that's how we proceed. Okay, and it happens that in this realization, the top particle goes to left and the bottom particle goes to right. Okay, so in the next configuration, you'll see this. There's no sign here, 2 here, and 2 here. Okay, so and now this side, they are active as well. So they need to relax, and in this realization, both particles go to the left, and both particles here go to the right, and keep doing that. And now you notice the observables that we defined earlier: the avalanche size, the duration, and area. So we see that we have one coupling here, and so that's why you have S is 1, and the arrow is 3 because now you have 3 sides involved, 1, 2, 3, involved in the avalanche. and you update, so you have two new size involved in the L1, so A is 5, and you have two relaxation, so F is 3, and every time you go from one configuration to next configuration, then the time advances by 1, so you have the duration increased by 1. Okay, and you keep doing that, so update that, and eventually you have no more active size, so now you have unquiescence again. So that is the illustration of how the abelian Manna model is defined and its action. Okay, right. So the detail of my study is summarized in this table. So I study on many different lattices of different dimensions, and so you have to see the fractal lattices and the lattices of regular dimension, and number of them, different structures, and the typical setup for the simulation. Okay, so these are the sample of the lattices that I use. So 4-dimensional limit, 4 one-dimensional lattices, 8 two-dimensional lattices. These are the lattices used in the ordinary critical phenomena. Then 3-dimensional lattices, 5 of them, and the fractal. So this fractal you have seen earlier in the first part of my study. So the crab, the arrowhead, and those things. Okay, and a few more. So just run quickly through this. Okay, so now we know the abelian Manna model. So what kind of behavior we would expect from this system? So theoretically, we expect the distributions of the observables to follow the power law with exponent tau. So that's the form of power law with exponent tau. So now we have 3 observables. So x can be either s, t, or a. Okay, so for that you have an exponent tau x. So you see this is the size of the event, and this is the probability, the probability to have events of that size. You see that in the log-log, this is plotted in log-log scale. So the nice feature about power law is that when you plot in the log-log scale, then you see a nice straight line, and tau in that case is just a slope of that line. Okay, but on computer we can only simulate finite size system. So we don't really see the very nice clean power law distribution, but we have the cutoff because the system now see the finite, the finiteness of the lattice. Okay, so we need to modify the power law distribution. It's not just a pure power law distribution. So we need to multiply the power law part by this thing called the scaling function. So you look at this scaling function, you see the argument, it is x over this xc. So x is the event size, so this probability to have event of size x. Okay, xc tells you the characterize the more or less the limit, the size of your system. So you see for small system, so you have this cutoff is about here, right? And for bigger system, then you have the cutoff extent, and the cutoff extent with the linear size of the system by this exponent called d. So for each observable, then you have the subscript x. So you have 3 different d's for 3 different observables. Okay, so look at this again. So when the system size is small compared to x, so this is going like 0. So this function does not do anything. It's just like constant. So you see a power law behavior. So that's why you see a straight line here. But when x is large, which is comparable to xc over there, then this function starts coming to play, and it behaves like an exponential decay. So that's why you see very drastic decreasing at the end of this distribution. And the bigger system size is, then you see a nicer power law distribution. Okay, so now for each observable x, then we have a pair of exponents. The tau, the distribution, the exponent for the distribution, and the d, which is called the finite size scaling exponent, because it tells you how the cutoff scales with the linear size of the system. Okay, so now you have the so we do the simulation for this system, for this model on different lattices. You can see 17 of them on 1, 2, 3 dimensional lattices. Okay. And for fractal lattices, 5 of them, and we also have a table. So we have 6, so 1 pair, 2 pair, 3 pairs, 6 exponent, and some other quantities. Okay, so through simulation, what have we learned from from this model. Okay, so previously it was proven by that the for the observables for the Avalon size observable, we have this scaling relation, the relation between the exponent d and tau for the Avalon size. So that proves that this holds for any lattices in 1, 2, 3 dimension. Okay, and the question was that now we have the fractal lattices, so would that relation still hold on fractal lattices? And it turned out that this relation no longer holds for fractal lattices, but it has to be generalized to this form, and we have to change the exponent to this dw called the fractal dimension of random walk on the lattice. And generally, on the fractal lattices, we have this thing is larger than 2. Okay.
This is the result you find yourself, right? In
Yeah.
your thesis. It's
Yeah.
your contribution.
Yes, and we link to the literature. So we just like we make connection, right? And this was published in 2 articles in the PIE. Okay, and we can also have some other scaling relation. So because remember we have three pairs of exponent, right? Size, duration, and error. So then we have another type of scaling relation, which is linked to this thing called the narrow choice distribution assumption. So the assumption says that, okay, now for one particular size of the observable y, then you find the expectation value of the other observable x. Then that expectation, that conditional expectation, scale with the size of the observable y that you chose. Okay, so from there, then you can work through the algebra, and you can work out this thing, and you have this relation. Okay, but that is in the early days of SOC, 1989. So that was made through that assumption. So it's not a mathematical necessity. So we need to verify that. We need to justify whether that assumption holds or not. And another scaling relation is for this thing called the compactness of avalanche. Which says that the finite size scaling for the avalanche error equals the size of the lattice. Okay, so through simulation with earlier, so we know that this scaling relation holds for the regular lattices, and now we extend that and confirm them to hold on general lattices as well, including the fractal ones. Okay, so this table just summarizes that and the physical interpretation of the scaling of the scaling relation. Okay, so now just a big recap, recap in the middle. So it is confirmed that the scaling of the abelian Manuel model is very robust. Again, various details of the lattice, like the nearest neighbor structure, because you see the lattice with very different topological structure and boundary structure as well, because we did some work but haven't published yet. So we know that when we change the boundary condition, we still see the same kind of behavior. And so from this result, we can justify the universality hypothesis, which is carried over from the ordinary critical phenomena to the self-finite sphericality, because this is a very well-established field, but this is not. So we hope that what we can learn from here, then we can apply to this this field, so we can get more insight into it. Okay, and again, all the scaling relations are extended and confirmed on general lattices. So fractal is not an exception anymore. Okay, so now I have shown you many things, the exponent, and many other things. So now you ask the question, why would we care about universality? Why is it important? Okay, it is important because it is the power of self-finite sphericality. Many features of very different phenomena that share, they're common to all those systems. They're very different, but they share some common features, common things. Okay, and with that power, right, okay, we can justify the analysis of simplify numerical models of very complex natural system, because you know natural system is very complicated. You have so many degrees of freedom, so many components. So how are you going to model it? So you need to identify those very core things that you put into your model and see whether it reproduce the behavior of the system. So at this point, I would like to quote this idea that everything should be made as simple as possible, but no simpler. And I think this is linked to the thing called the Ockham razor. I'm not sure if you have heard it or not, but that is the idea. So we just need the minimal amount that is needed. Okay. So now, maybe another 5 minutes or so now we know that we performed a study of the in-depth study of the Abelian-Manner model on lattices of many different systems. So what can we say about the exponents in all dimensions since we have the data available? So just make a quick and dirty study. Why not? Okay. So we list the exponent again because you know that on regular they're just the same. So I just put the dimension d, even though we study on many different lattices. Then for regular dimension, so this for the fractal lattices of different dimension. Okay, so we list the table there. So we compare them. Okay, I'm sorry again, I cannot see. Okay, so you can correctly see the points over there, right? So this is for the exponent, the finite size scaling of the epsilon size. The finite size scaling exponent of the epsilon size, this is the dimension of the lattice. So I plot them, then you can see actually they're quite scattered, but you can still see the trend going up, right? And you can identify the 4 points for the regular lattices, 4 of them, 1, 2, 3, 4. Okay, and they seem to fall on a line, so I can draw a line. But how about the other points for the fractal lattices? Not very nice, right? So I'll try the other way. So now I plot the d times 2 minus now against the dimension again. So nothing, I'm very sorry, but you can see my screen. And similarly, so I plot this thing against d. Still nothing very nice.
You can actually go out of the slideshow, try to enlarge the figure.
I think it's a problem with the projector, it won't help anymore.
It could be your lines are too fine.
Yeah, the lines are too fine.
So you enlarge the figure, it would show perhaps.
That's the
If
default
you
line with
interrupt your
MATLAB,
slide
right?
presentation and just manually click on the figure, drag it, make it bigger.
Okay, anyway, I don't think that is very important. Let's move on. Okay, but something interesting is going to happen in the last figure. Okay, so
I can see.
Because
You can see this one, right?
They have not read your thesis at all, you know.
Alright, okay.
Yeah.
Would I have extra time for doing that?
You just interrupt your presentation presently, click on the figure, drag it bigger, finish.
Okay, anyway, it comes already. So this is the one. So you can see this thing clearly, right? I hope, from the back. Right, so the idea is that now I rescale my exponent by the dimension of the lattice. So you see this is d, big D times 2 minus tau, and this is big D, so I rescale by the lattice. So now everything falls nicely on a straight line. Okay, so I can fit this line and with some regression coefficient of very close to 1, which has a very good fit of this, that, okay? And okay, this is much better. Okay, so the analysis suggests that there exists a relation between the exponents and the dimension of the lattice. Okay, so this is the data for the d rescaled by d and the fractal dimension of random walk rescaled by dimension of the lattice. Okay, so if you're actually interested, then you can know that for the dimension above 4, which is the critical dimension of the system, we have this thing called the mean field exponent. So actually they also fall this thing. And you see the mark of this thing, it is the point where you have the critical dimension of this model, which is 4. Okay. Right. So but we are not happy with that because actually the thing is not very good yet. So we try some other things. So we arrive at this. We did further investigation, and we show that d scaled by d actually fit very well to that expression. Okay, and this is plot of this d against tau. Now you see we did the arrow bar, so they fit very well. Okay, but that's it. I must admit that I cannot provide you with further insight into this kind of relation, but it is remarkable, I believe. And actually, the referee of that paper, he agrees as well. Okay, and similarly, you can do for the avalanche duration as well. So we also find the same kind of behavior. Okay, so these facts pose the question of the existence of a very general scaling relation that could capture any lattices, that could capture any lattice and is true in all dimensions. Because you see, in this thing, this is a mixture of the regular integer dimensional lattice and the fractal lattices. So they agree very well to one another. Okay, and this presumed relation might be linked to some unknown underlying physics of this model and maybe SOC in general. Okay, so that is more for the numerical study. So I also did some analytical study. So I could calculate the first moment of envelope size by mapping the process in the Wheeler-Manor model to random walk. So I can argue that, so I arrive at this form. So the first moment of the envelope size S is half an ensemble average of the resonance time of the particles on the lattice, because the particles in this Wheeler-Manor model perform random walk. So we can do that, and we achieve the exact expression for S, and we compare that to the numerical simulation that we have got, and they agree very well. And that confirms our simulation as well. And actually, Michael Lerner, he went one step further, and he could achieve this more general form. But this is only the form, but it's very difficult to implement, because for a general adjacency matrix, it's very difficult to get eigenvector, the eigenbra, and this eigenvalues of the adjacency matrix. But the formula is available. Okay, but I think I'll just skip this thing. It is a model that I invented and some development that I have done. Okay, so now we come to a conclusion. So this is the highlights of the results that I have achieved through this project. So I came up with the novel idea of fractal generator, and the fractal generated by that system, they can count the two-dimensional space. And I also show some kind of top application to the Goldstone morphology, and that is one. Another application is that it can you remember the invariant standard points in the fractal, right? So they can form the fractal lattices that could be used for any lattice model study. Okay. Then in the second part for the self-finite sphericality, I show the generalization of the scaling relation for the album size. Instead of 2, so now we have to replace that by the DW, the fractal dimension of random walk. Then we also observe the scaling behavior of the system in non-integer dimension with the head of fractal lattices. Okay, and we also show the universality of the critical exponents and moment ratio and the motion and the moment amplitude. What it means that the model on different lattices of different structure in the same dimension, they are the same. So that is what meant by the universality in this case. And we also show the relation of critical exponents in all dimensions, which is the fit that I showed just now. And this actually highlights the role of scaling against n, because you remember in that relation, I rescale the exponent by the dimension of the lattice. And you remember that the exponent formerly, it was achieved by scaling against the linear size of the system. So now when you rescale by the dimension of the lattice, so actually you're doing the scaling against the n, the total number of size on your lattice. Okay, and this is the part that I skipped during short time. So it is a solvable model that I developed to study the exact PDF and the scaling laws. Okay, so what have been addressed? So 3 main questions have been addressed in this thesis. So the first one is that how different are the behaviors of the SPC model on fractal lattices from those on the regular lattices. So we show that they don't really follow, because now instead of d times 2 minus tau equal to 2, so we have to replace that by the dw. Okay, and the second question is how robust and universal the critical behaviors of an SOC model itself. Because usually in literature, people they study on the same lattice and they study different models and find the same behavior. But now we ask the question the other way around. So we ask for the same model but different lattices. We see how robust and universal. Okay. And the third question is that are there any relations between the behaviors of the models in different dimensions, including both the regular integer and irregular integer lattices? And one of them, I have shown you the fit of that relation. Okay, and it could be summarized in a series of publications. Okay, so now what? So this is more like the outlook. So I hope that I have convinced you that SOC is a worth investigating phenomena because it exists as a robust phenomena with unique features distinct from the other phenomena that we have known. And it is important for providing the understanding of the long-range correlation and critical phenomena without tuning the system. Because this can be seen that when you drive the system, right, in the two models that I showed you, you just keep throwing the particles. You don't make any fine-tuning of the system at all. There's no parameter for you to tune the system so that it reaches the critical state. Okay, and of course, this is for researchers. In this field, it is that currently there is a lacking of the proper theoretical framework that can explain the observations and produce the features and justify the assumptions in the SOC. So that's why we keep doing research on this field. And the ultimate question, I think, in this field is that we need to ask what are the necessary and sufficient conditions for self-organized critical phenomena. Okay, and so now look at this. So I have two parts in my thesis: fractal and self-organized criticality. So in the spirit of complexity and complex systems, so both of them boil down to this same idea. So we have simple rules applied repeatedly, lead to emergent complicated patterns and or behaviors both spatially and temporally. So you can show you. So I have shown you simple rules in the case of fractal or in the case of the same power model applied repeatedly. Then you can see the emergence behavior. And now I think we are in this era of the complexity science. So we need many theories like chaos, fractal, or self-organized criticality in order to understand the complex nature of the world surrounding us. Okay, so and this is only my starting point. So my general interests are to study the phase transition and scaling phenomena in the complex system and link different complex systems through the common shared emergent features by this the power of this universality, and also to build a model and theory based on the observation of the microscopic process from the data. And my collaborator is Gunnar Presna from the Imperial College, and I'm very grateful to them because the entire simulation was run on their cluster full time. Okay, and I was funded by NTU. Okay, so I think that's it. Thank you.